Palm calculus is the sophisticated name of something that has to do with queuing theory, with simulations, with stationarity, but that is related to something more mundane that I call the importance of the viewpoint. We will do it in two parts. We will first do the easier and more intuitive part, then we'll give the mathematical formula that capture the phenomenon that we will describe here in a more rigorous and formal way. The importance of the viewpoint is illustrated by this. Airbnb is generating a lot of trouble in many cities because they increase the prices of rentals in very popular touristic cities. It's more advantageous to rent your apartment to tourists than otherwise. And so there was a case against Airbnb in New York City, in other places perhaps also, where Airbnb was asked to justify whether it's true that it's really flat sharing or whether it is a hidden form of hotel. Right? If you have a hotel, your interest is to rent your rooms every day of the year, right? If you share your flat, you rent it when you're on vacation, or if you need money, you agree to leave for a few days to rent it, so it's different business. So they were asked to give statistics on the occupancy of every listing. A listing is an apartment or a room. And they were asked, what is the occupancy? Occupancy means the number of nights during a year in which it's rented. And Airbnb said the median is 40 days. 11%, which is a proof that we are really an apartment sharing system and not disguised hoteling. Then a consumer association called Inside Airbnb asked people who rented through Airbnb to give their own statistics on their own website, not through Airbnb, and they found a median occupancy of 165 days a year. So the way and that's the difference. So Airbnb says 11%, Inside Airbnb says 40-something%. And this, of course, is more a problem. It means really an apartment that's rented, roughly speaking, half of the year. You can't really claim it is apartment sharing. It is really doing business with renting to tourists. Right? Who says the truth? Right? Is one of the two lying? That could be. We had companies in the past that lied, like Volkswagen, who lied on the diesel pollution test, so that can happen. But here, as we will see, it's not the case. Both are true, at least as far as we can judge. It's just that what they call median occupancy is not exactly the same, although it's exactly the phrase in exactly the same way, but it's not the same. So the topic here is I'm defining a metric for my performance evaluation, here evaluating Airbnb occupancy. I need to define not just whether it's a median, a mean, and what it is, occupancy of rooms, but also how I sample it. How do I measure this? How did they measure this? How would you imagine that Airbnb obtained such a number? Yes?
Nights that were booked on the website and compare that to the number of apartments they have registered. Then you have the number of night available nights that were taken.
So accumulate the number of nights that are rented and compare to the number of apartments. That would give you something like a mean. Perhaps that would give you the mean number of nights per apartment, but that would not give you the median. For the median, you need more information. You need the distribution. You need to say 50% of the apartments are rented less than 40 days. 40% of the apartments are rented more than 40 days. So probably what they do, or what would you do if you would work at Airbnb here? So probably what they did is they looked at all the list of apartments they have. Hundreds of thousands of apartments. For each of them, they looked in the past year how many nights they were rented. And then they sort them from A to B, and they look in the middle. What's the value in the middle? And that gives 40 days here. Inside Airbnb probably did something else because they are consumer based. So they ask people who say, when you are in a rented apartment, you ask the owner, how many nights did you rent it last year? Right. And then you report in Airbnb how many nights. That's probably one way to do it. Another way would be to have a complete information of all the rentals, but probably they don't get this here. Here there's a difference in viewpoint. Here we take an arbitrary apartment and we ask, for an arbitrary apartment, what's the distribution? What's the median of that distribution? Here we take not an arbitrary apartment, but we take an arbitrary customer. We ask an arbitrary customer how many nights were rented in the apartment where you are now. Right. So that is probably what they did. So this difference is a difference of sampling. Here's another one. This one is a made-up example, but it's very similar to what you could imagine with a train company. So it's about a train company called Sovrail that tracks all the trains, and as everywhere for every train company, people complain about trains being late, and they say, but the number of trains that is late is less than 5%. So excellent performance. Again, a consumer association does the same thing, and they say, but 30% of our consumers complain about the train being late. Right? Could you also explain that through a difference of sampling?
Software took all the incidents they had in all the trains and divided by the number of trains they have. Mm-hmm. And that doesn't take into account, and it's true that a lot of trains have no people inside or children inside. Mm-hmm. And more people talk to people. Mm-hmm. So they more probably talk to people in big trains at busy hours. So these people don't see trains that have more problems than them. They mostly see peak hours with lots of problems.
Exactly, that's probably what has happened. So Bordeaux Consume gives a statistic which is per consumer. Here it's per train. Now, probably the trains that are late, as you said, are the trains that are at the busy hour and that are densely packed with lots of people. That's why they are late. Probably they need to wait more at the train station because it takes more time to get on and off. Since it's the peak hour, the frequency between trains is larger, so any incident will have a rippling effect that can cause delays. So it's more like probably here the 5% are all trains that are at the peak hour with lots of people in them. So that might cause this here. What we will do is we will see, well, the very first important thing is to become careful when you see ratio, percentage, probability, median. What is the sampling? By which method is it sampled? So what is an arbitrary unit? An arbitrary train, an arbitrary customer, an arbitrary trip. What we will do is we'll see how we can reconcile the two to verify whether the two are true, and this is called pound calculus. Pound calculus will do what's the mathematical relation between two quantities that are sampled differently here. For that, we will need to introduce some vocabulary. Let's start with a very simple, and the classical use of pound calculus has been to study queuing theory. So in the language of queuing theory, we have what is called events and time averages. Events are the times at which something of interest occurs. For example, an arrival of a customer to the queue. Right. So we consider that there is an event clock, so it's a sequence of times at which some specific changes of state of the simulation occurs. Right? So we have to decide what we call event. For example, I could call event an arrival. Once I have decided that I call event an arrival, I have a sequence of times here, which is called our event clock. And then if we have an event clock, we can do what is called an event average statistic. We can sample the system at the times of this clock here. For example, if the event clock is arrival of job into a queuing system, and I sample the queue size, and I take the average of this by this clock, I obtain what we can call the mean queue length seen by an arriving customer. When a customer joins the queues, she sees a number of busy customers ahead of her, and in average, the number you find is this here, right? Which I can call, if I do a simulation, if I do a very long simulation, I call capital N the number of ticks of this clock, the number of arrivals. Then from the n plus 1, I start numbering in 0, unlike MATLAB. And then the queue size just before the event, the clock ticks here, is what I can call the queue sampled by this here. And if I want to estimate it by a simulation, I will do 1 over n plus 1, the number of events, the sum of the values I have sampled here. I could sample things differently. I could sample over what we can call an arbitrary point in time by saying my simulation has run from the beginning to the end, for example, from t0 to t capital N. And I could ask, what is the average queue length? It's the average queue length. We can think of it as being seen by an inspector. Who is the inspector? The inspector is the poor guy who would be sitting in front of the queue, and every second he is measuring what happens and does the integral of this and divides by the duration of the time. So that is the average queue size. Both are legitimate average queue sizes, but they are defined differently. We find some of this difference of sampling already. We had an example of a formula where we had different sampling viewpoints in queuing theory. Little's formula says the average number of customers in the queue is the arrival rate multiplied by the average residence time. The average number of customers is a time average, right? The average residence time is an average per customer. So it is something that is more complicated than simply a formula like this, but something that's attached to a customer. So I compute one value of a residence time when a customer leaves. I need to tag the customer with its arrival rate. When the customer leaves, I read what time it arrived, what is the time now, and I have one value at this time here. So it is also an event average statistic. And we found a formula between the two. That's an example of pound calculus formula. Let me start with a much simpler case here than Little's formula. It's an example inspired by what is called a gatekeeper. A gatekeeper is a processor that is in charge of handling a job before giving it to the rest of the computer or the data center. This is used in many things for load sharing. This is used also, for example, for avoiding congestion collapse. You make sure the job is first. You screen whether you really want to do the job. If not, you throw it away. So I assume when a job arrives, it needs to be handled by the gatekeeper. And for some reason, there are two gatekeepers here. The gatekeepers wakes up a bit irregularly because it's also busy doing other things. It wakes up at time 90 or 100 or 190, 200, etc. And when it wakes up, when it's at the red time instant, the job will be assigned to some processor where, bad luck, the execution time will be 5,000 CPU cycles, for example. If it comes at the green time, the job will be assigned to a processor that will give you 1,000 cycles here. Assume you are the designer of this system. You could say, when a job arrives, it will be assigned to one of the two processors here. One processor, bad luck, it's busy, but there's no way I can do otherwise because I have other things to do on my machines. It will have this time. So in average, the average of the two is 3,000. The execution time is 3,000 CPU cycles from this. This is the viewpoint of the system designer that says, I have two processors or two cores, and the average is 3,000 here. Now, if I take the viewpoint of a job that arrives at an arbitrary point in time, that we see that jobs the probability that if you arrive at a completely arbitrary point in time, one way to think of an arbitrary point in time for this simple example is to assume, because this example is completely periodic, is that you arrive in one interval uniformly anywhere in the interval. There is a difficulty in defining what is an arbitrary point in time, which is an embarrassing thing of probability theory. Right? An arbitrary number between 0 and 1, what does it mean for you? Yes, it means a random number that follows a uniform distribution between 0. An arbitrary point in time, what is it? Inside the time interval, you can define between 0 and 1, I can define an arbitrary point in time. But an arbitrary point in time without specifying the interval does not exist, because the uniform measure on the set of real numbers is not a probability. You cannot rescale it to make it a probability. So you cannot say what it means to arrive at an arbitrary point in time other than by bounding it. There's a trick to go by that we will see. We will see that the arbitrary point in time is the same, gives the same sampling statistics as if we would observe the system by arriving according to an external Poisson process. So you assume the most random way of choosing a point in time is according to the Poisson process. But you need to define the rate. You can do it very frequently or very rarely. If the system is stationary, the rate will not have a role. So one way to think of it is to think of an inspector that arrives at arbitrary point in time, or here a job that arrives according to a Poisson process in this thing here. If you arrive according to a Poisson process, then you will pick, because the Poisson process is completely homogeneous, the probability of arriving in any interval is the same, wherever the interval. Therefore, it's proportional to the interval. The probability that, given that you arrive between 0 and 100, you arrived before 90 is 0.9, 90%. So an arbitrary job will pick this with probability 90% and that with probability 10%. So in general, a job is very likely to find the 5,000, and in fact the average is very close to 5,000, is 4,600. A few years ago, that was exactly the train between Geneva Airport and Lausanne. The arrival is you or me arriving from the plane. Planes are, we can assume, asynchronous with respect to the train schedule. Even if you try to synchronize them, they will be late. And then between Lausanne and Geneva, the train schedule, at least at the peak hour, is periodic. But there were, in the past, 3 trains within 20 minutes, and then no other train during 40 minutes. Right. And the train that was, so you were most likely to be in the interval of 40 minutes, so your average waiting time was close to 20 minutes, even though you had 3 trains an hour, which would mean an average waiting time of 10 minutes. Plus the train that is, the first train that was at the end of the 40 minutes was the slower one. The train that stopped several times. So you were more likely to wait a lot and to take the slower train. But CFF would say we have 3 trains an hour and 2 out of 3 trains take 45 minutes. But the train you take takes 55 minutes and you wait more. So that's another example of this. So we have here 2 viewpoints. Here it's very easy to analyze them by hand. What we will do is the maths of Palm calculus, how we can reconcile the 2, and this will illustrate the general type of formulas we can have between the 2. The method that I propose here is, I call it the large time heuristic. It is simply what we do when we do a simulation. So one way to reason about this, heuristically, is to say, if I do a simulation, how do I measure those 2 things? And then try to compare the different way of measuring things here. So the setting here is I have an event clock with the times shown in blue, T1, T2, T3, T4, etc. And there is an interval between 2 event clocks that I call S. So S3 is the interval between T2 and T3. There is also an interval S2 here, S4, etc. that is not shown. When T1 fires, when this clock ticks, we choose a random value, x1. If it's T2, we choose X2, etc. So there's a sequence of choices we do here. And here it's not very random. It's when it's a red time instant, we always pick the same value. But in general, we could have those things random here. So the first thing is, how would I compute those two averages in a simulation? So I'm casting myself in a slightly more general setting where I would allow the time intervals T1, T2, T3 to be random, and the values of x1, x2, x3, etc. to be random. Well, the designer viewpoint would consist in saying, I have capital N blue events here, and the average of the execution time is the average of the x bar, sum of the xn. The customer viewpoint is a bit more tricky. It consists in saying I have a long simulation time that lasts for a total time capital T, not to be confused with T1, T2, etc. So the simulation goes from 0 to T here. And then I can say a job arrives at any arbitrary time here. So I'm not simulating the arrival of a job. I'm just asking, if a job would arrive at a time little t, what would be the execution time it would pick? The execution time would be the xn for n, which I call n plus of t, which is the index of the interval in which, of the next interval, the next arrow after time t. So for this arrow here, n plus is 1. If a job falls here, n plus would be 5. If a job falls in this small interval, n plus will be 3. So with this notation, I take the integral, because I assume the job can arrive with the same probability in any time interval here. So this is how I could evaluate this in a simulation here. Now if I massage this a bit, I can say that my integral here, I can break it into the integral over all the intervals that are shown here, right? So I have an alternation of interval from green to red here. This is what I'm showing here. Now, during one interval, the n plus, during the first interval, n plus is 1. So this is simply x1 here, etc. So this sum here breaks into t1 x1 plus s2 x2, etc. So this sum here. So the second way, the customer viewpoint, is simply 1 over t, the sum of the duration of the nth interval multiplied by the value we pick when we arrive in the nth interval. Which is fairly intuitive. It's just capturing the fact that the probability that you pick number 2, for example, is proportional to the duration s2 here. But you see that when I'm doing this, I'm not doing a probabilistic analysis. In particular, when we do probability, we have to ask questions like, are we exploiting something of the distribution? Are we exploiting the fact that it's memoryless? Are we exploiting the fact that things are independent? Here I'm not. I'm just saying I do long-term averages, I sum up things, and this is true whatever the distributions, whatever the independence. Now, once I have found this, well, I can simply re-massage it by saying this was an average over time, 1 over t. Now what is t? T is equal to n multiplied by lambda. Well, lambda is the frequency at which the clock, this event clock, ticks, right? It's the number of ticks per time unit. Over a long simulation of duration t, n over t is lambda here, right? And this thing here is an estimation of the covariance of S and X. Is an estimation. It's a sample estimate of the expectation of SI times XI. So it is what we can call the sample covariance of S and X plus the product of the mean, because by definition the covariance is this minus the product of the mean here. In other words, we see that the viewpoint that is experienced by an arbitrary job is equal to the viewpoint that is thought in their head by the designer. Of course, you are smart designers, you would not say this, but when you design things, you perhaps don't have this clear drawing on the board. You're just lost in your code and your design. You say, I have 2 jobs, I have 2 processors, so that's the kind of things that we would naturally be led to doing. So the relation between the two is this one. WC is equal to lambda times the covariance plus WS. That's a Palm calculus formula, and what we see is very typical. We have the intensity of the clock that occurs in the formula here. Right. So, which we can express in this form. Sorry, where am I? I'm lost here. We can think of it as we have a random variable Sn, which is the time of the interval we're in, and we have a job duration, which is the job duration we obtain when we fall in this interval. And this is simply the covariance of S and X, if we assume those are random variables here. In which case do we expect WC, so the per job viewpoint, to be larger than the designer viewpoint? And we have unanimity and majority, because we have one answer. Here, we can do it in 2 ways. We can look here intuitively. That's the system I've shown before. When we arrive in a large interval, we have a large value. Therefore, we are likely to find to be worse off than in average, right? We don't take the 2 with equal probability. Here it's the other way around. When we're a large interval, we find a smaller value here, which is also captured by the covariance. Here we see when Sn is large, Xn is large, so the covariance is positive. Here when Sn is large, Xn is small, right? When Sn is small, Xn is large. So there is negative correlation between the two. If there is negative correlation, it's the other way around. So that's an example of Palm calculus where the 2 viewpoints are different. They might even be the same if the covariance would be 0, which would be true if, in particular, if they're independent, which means perhaps the intervals are irregular, they are random, but the choice of the processor and the resulting execution time that you have is independent of what has happened to this interval. If that happens, then the 2 viewpoints would be the same here, which is probably what is intuitively assumed when we use the designer viewpoint. If we assume things are independent, I have 2 processors, 2 types of execution frameworks, a random job will pick one of the 2 with equal probability. That's what we could assume, but here it was not the case. So what I've explained is the large time heuristic. It's explained in the context of times. And as I mentioned, a first thing to observe, it's a robust method. It's independent assumptions on distributions and on independence here. If there is independence, we can find some formulas, but we have formulas that are more generally true here. Let me see how we can solve other cases by other viewpoints that are all variants of this one. So it's useful to think that a clock is not necessarily just in time, but if we order a thing in some arbitrary, according to some line, for example, one thing that has been studied a lot in the internet is the distribution of flow sizes. This is very important for dimensioning data centers, for also dimensioning networks. So we have discussed yesterday that flow sizes are typically following power law, Zipf's law, or even are heavy-tailed. So finding some properties of this has been studied a lot. Now, there are different ways we can sample a flow size. So what is a flow? Well, in the internet, typically a flow is defined by a combination of source, destination, address, and port numbers. So an interaction between processes. You could ask for an arbitrary flow, what is your size? So if you have all the logs of a data center, you can see whenever a socket was opened to transfer a sequence of objects, how many bytes were transferred. That will give you, for this flow, the size, and then you can do a histogram for all the flows here. But you could do it also for an arbitrary packet. You could say, and this is perhaps the viewpoint that's interesting when you use things in routers or in the internet, you could say, how long will this flow last, or in number of bytes, how big will this flow will be? So you could ask an arbitrary packet, what is the size of your flow? Of course, the packet doesn't know, and if you see a packet, you will know only when you've seen all the packets of the flows. But this is the kind of questions that is important for flow routing and load balancing in the internet. Here's, for example, a paper of Jennifer Rexford and co-authors that has studied this issue and has plotted graphs based on measurements. There are different kinds of flows depending on you call the flows. The flows I've mentioned are the port-to-port flows. You could define a flow differently by saying it's an interaction between two exactly same hosts, not necessarily the same port numbers here, or also subnets or nets, etc. Here, there are two groups of histograms, right? Those are cumulative 1 minus the CDF, right? On the y-axis is proportion of flows with size larger than X packets. So it's measured in packets, not in bytes. On the x-axis is the number of packets. So this is what we call the complementary CDF, 1 minus the CDF. Which one is for the per packet viewpoint? Which one is for the per flow viewpoint? She measured both. And unanimity on A, which is the correct answer, because if I ask an arbitrary if I do my simulation or my statistics, my measurement, I look at all the packets and I ask every packet, what is the size of the flow that you belong to? If a flow is large, there will be many packets that will be in this large flow. So there will be more packets that belong to large flows than flows. Right? In the worst case, if there's one huge flow that covers 80% of all the data, there is one flow that is very large, all other flows are small, but there are 80% of the packets that are in a large flow, that have this large answer. So this is the correct answer is A. But we're interested not just in the qualitative correct answer. So that's the per packet viewpoint here, right? So but also finding is whether there is a relationship between the two. So to find this relationship, I could call the PDF of the distribution when I sample at an arbitrary packet. So F of S under this viewpoint in my statistics is the number of flows that have length nth divided by the capital N, the number of flow. And per packet, I do the same, is 1 over P, the total number of packets that I have in my data sets, multiplied by the number of times that a packet declared that it belongs to a flow length S, right? So we can apply the same trick as we have seen before. If I do a simulation or I have large data, this is how I would compute those two statistics. The per flow statistic will be 1 over n, the sum of the length of the flow. So Sn is the length of flow n. And per packet, it will be 1 over p, sum over p of the length of the flow that packet p belongs to. Right. And if we massage this, or one way to illustrate that, as here is how I can see this. I have here 3 flows, a number of packets. I put back-to-back all the packets to make it look like a line. Then I have exactly the same problem as I had before. If I consider the clock, the end of a flow here, I will have the same kind of things. The average done per packet is 1 over P times S1, the size of the first flow, as many times as there are packets in the first flow, which is also S1. So that's S1 squared. For the second flow, I have the length S2, and this answer is given also S2 times. So in average, the answer I will have is 1 over P, sum of the Sn square. So we find, funnily, we find a square here. So if I compare the two, by massaging the two, I will find that the per packet viewpoint will be equal to the per flow viewpoint plus 1 over the average size, 1 over the per flow viewpoint, which is the average size of a flow, multiplied by the variance of the size of a flow. Here. So that's another example of PAM calculus formula. This one is more biased than the previous one because the variance is always non-negative. So it means that the average size of a flow is always less than the average size of the packet of a flow experienced by an arbitrary packet. If we sample per flow, the average size of a flow is less than the average size if we sample per packet. And the only way they could be equal is that all flows have exactly the same size. The variance is 0 here. So any variability in the flow size will introduce a bias. So that's an example where the two viewpoints are perfectly legitimate. Perhaps the more natural viewpoint is this one, but for other applications, the viewpoint of interest may be this one. And if you don't think that there is a viewpoint or a sampling problem, you are likely to pick randomly one of the two. And the two different viewpoints will never agree because here there's a systematic difference here. We can do exactly the same analysis for the PDF, and we obtain this formula that says, here I was asking what is the average size if I sample by flow. Instead of asking the average, I can do whatever statistic. I could do the histogram, for example. The histogram will give me the PDF here, and I have this relation. The histogram that I obtain if I do things per flow, for example, here I have two flow sizes, 2 and 5. So I have one flow of size, 1/3 of the flow is of size 5, 2/3 are of size 2. That's the histogram I obtain. That's the FF here. Now I can ask what's the viewpoint from an arbitrary packet, and of course we have now 5 packets that are in a flow, so 5 versus 9, so 55% are here. And the mathematical relation that can be obtained by exactly the same reasoning, but with a bit more notation, is exactly this one. The per packet viewpoint is proportional to the per flow viewpoint multiplied by S. So the probability that an arbitrary packet is in a flow of size S is equal to the probability that an arbitrary flow is of size S multiplied by S. Right? Which sort of makes sense because you have S packets in a flow of size S. Of course, we must have a normalizing constant because if I multiply by S, this is no longer a probability distribution here. So, to conclude for today, back to Airbnb's paradox. If I call f of S the proportion of objects that are booked S nights per year, and the occupancy seen by an arbitrary traveler, which is the proportion of bookings that occur in an object booked S nights per year. Right, so here I'm sampling per traveler, here, right? Or per night, sorry. What kind of relation do we expect? So here we ask an arbitrary booking, or not. So let's say, assume an arbitrary night. One booking is one night. If you stay 3 nights, it's 3 bookings. If you ask for an arbitrary night, what is the number S of nights that this object that you booked was booked in this year? if you are an object that's booked all year long, then the answer is 365. And then we do a histogram of the answers that are given by asking each booking or by asking each object here. Who says A? One. Who says B? Who says C? Okay. Well, it's precisely the other way around. Right? If you ask a booking, you're more likely to find on the booking that is one of the objects that is more booked. Right? In fact, you can do, you can do the same mathematical derivations. You put, is the same reasoning as with files and packets, and you put a line when there is a booking for this object, right? You ask an arbitrary booking, what's the size, how many nights are there per year in the object that you were booked in? Then we will find the same relationship here. So the median of one distribution is 40, the median of the other is 165. This is completely compatible here, and that has been studied by the paper that I give in reference. So reconciling these two viewpoints was one of the objects of this paper, and showing that, well, nobody was lying here, but when we read statistics in the press or here in court, it's worth discussing those things here. Voila. That's all we will see for today. Thank you for your 10 minutes of patience of overtime. That's all we'll see for today. Next lecture, which will be after the Easter break, we will do a formal theory that will explain things like this. For explaining things like this, we don't really need a formal theory. I mean, I've given all the elements that you can use to derive your own formulas very easily. But in some cases, as we will see for what is called perfect simulation and for understanding what is called freezing simulation, so non-stationarity that is not as obvious as systems blowing up. So this is what we will study after the Easter break.